32nd lecture and the topic is power amplifiers that we started yesterday. We continue discussion on power amplifiers. Yesterday's lecture was mainly concerned with determining the Q point and the distinction between DC load and AC load. For amplifiers which have to handle a signal, the DC load may be different from AC load, and AC load resistance is usually smaller than the DC load resistance. And these considerations, the other considerations that come into play is the maximum allowable VCE, the maximum allowable power dissipation, the maximum allowable collector current I sub C, the minimum allowable I sub B, the base current, which is 0, and the saturation line, that is the line below which the collector base junction is no longer reverse biased. And we saw that in the I sub C versus VCE characteristic, the power amplifier operation should be restricted to a region like this, a region bounded like this. This is the saturation line, this is the maximum I sub C line, this is the PD line, the power dissipation line, this is the maximum VCE line, and this is the minimum I sub B line. All right. So this is the region within which the operation has to be restricted. Now in this region also, the choice of Q point, as we had illustrated last time, has to be done quite carefully, and the transistor, in order that you get the maximum possible power to the load, the transistor has to be driven to its ultimate limit, which constrains that the Q point must be on this line. Q point must be on the P sub D line, that is the line on which VCE I sub C equal to a constant P sub D. Here also, wherever you choose the Q point, the load line should then be tangential to this hyperbola. Now you can choose various Q points and find out what load is required. The load will now be determined by whether you want a maximum voltage swing or maximum current swing, and we decided last time that because of distortion considerations, perhaps the voltage swing should be maximized. Perhaps the voltage swing should be maximized. All right. Let's with these few preliminary remarks, let us now illustrate with the help of an example how one goes about designing a given power amplifier. The specifications of a given transistor which is to be used under the circumstances is that I sub C max is 1 ampere. All right. VCE max, these are all specified by the manufacturers. VCE max is 50 volt. Now this is no surprise because you have to deliver power. Power transistors usually have a much larger rating than voltage transistors or current transistors. PD max, that is the maximum power dissipation, is specified as 5 watt. The minimum beta min as specified is 30, and in addition the load RL is specified to be 750 ohms, and the design is required to be done in such a manner that maximum power is transferred to the load, maximum possible power. The circuit is the usual self-biased circuit, that is you have an RE, then R1, R2, R sub C, this is plus VCC, and the load is specified 750 ohms, and it is also specified that the load should not carry any DC. In other words, you have to isolate the load by means of a capacitor. So this is the load RL. The DC load, well, this RE is to be bypassed by a capacitor. This is the blocking capacitor, and then the signal is to be applied through another capacitor. All right. This is the input signal, input AC, let's say VI. All right. This can be input AC source VI. This is a blocking capacitor. This is a blocking capacitor. This C sub E is a bypass capacitor because this bypasses RE. In other words, for AC, RE behaves as a short circuit because of the capacitor CE. Now you see, the power amplifier design has to be a compromise between many factors, many situations. These maximum specifications, these three, must not be exceeded. Number one, under such circumstances, how do you choose your Q point and the AC load in order that maximum power is delivered to a part of the equivalent AC load? The equivalent AC load obviously is the parallel combination of R sub C and R sub L, and we don't know, we know RL, we don't know RC. RC is to be determined. All right. So power will be, some power will be wasted in RC, the rest of the power will go to RL, but what you pass to RL must be the maximum possible one. There is some power wasted in RE also because some DC passes through this. All right. And in addition, you see the DC, at DC the effective load is RC plus RE. If beta is large, then the effective load at DC RL does not come into operation. So the effective load is simply RC plus RE, and the effective AC load is RC parallel RL, which obviously is less than RC, and therefore the AC load is less than the DC load. Now in order to see how to choose the Q point, let's appeal to the characteristic curves of the transistor, the I sub C VCE characteristic. All right. This is I sub C in milliamperes plotted versus VCE. You notice the nomenclature, small I subscript capital C. This denotes the total collector current, that is DC plus any signal current. Similarly, small VCE is the sum of capital VCE, that is DC, plus any AC. AC will be denoted by small v subscript small c small e. Similarly, I sub C is capital I sub C plus small I sub small c. All right. IC versus VCE characteristic, and these are the usual characteristics, the spaced at equal intervals of I sub B. This is for 0 milliampere, this is for 2, 4, 6, 8, 10 and 12 and so on. This is the saturation line. This is the saturation line. Your VCE should not go below this. Then the base collector junction shall no longer be reverse biased, and you should not exceed a certain maximum VCE. VCE maximum is specified to be 50, and therefore this is your ultimate line. This line, what did we call this line earlier? The D line, or what was it called? Doesn't matter. There was a line here. So your VCE max is 50, therefore you must not exceed this voltage. All right. Now the power dissipation maximum is specified as 5 watt. So what you do is you draw the 5 watt hyperbola on this characteristic, which is the green line. This green line gives the plot of IV, that is I sub C times VCE, equal to 5 watts. So it's a hyperbola, and the Q point must be located on this hyperbola. All right. Now since 50 is the maximum allowable VCE, and you want maximum voltage swing and maximum possible current swing, well, in between the two we choose the maximum possible voltage swing because the characteristics are more linear in the region of high voltage swings rather than in the region of high current swings. There are many non-linearities here. Alright, so we allow our VCE, you must understand this carefully, we allow our VCE max to be absolutely the limit, 50 volts. Then what should be the Q point? If we want maximum possible swing, obviously the Q point should be at approximately half of VCE max. That does not mean that you can go up to 0, no. You cannot go up to 0. Why not? Because there is a saturation line. Alright, but approximately approximately your Q point is at 25, and therefore at 25 if you draw a vertical line, this touches, this cuts the PD hyperbola, that is the green power dissipation hyperbola at this point Q, which should therefore be your Q point. Agree? This is how you determine your Q point. Now you know your Q point and you know what is the maximum VCE, and therefore you know the AC load line also. This orange line is the AC load line. Is that clear? From which you get the effective AC load resistance as voltage swing, which is 25 volts, divided by the corresponding current swing is 200 milliampere, that is 0.2, and therefore what is RAC then? The effective RAC shall be equal to 25 divided by 0.2 ampere, which means 125 ohms. Is that clear? How you determine the effective RAC? Now what is effective RAC? It is the parallel combination of RL and RC, where RL is specified as 750 ohms. Alright, therefore you know what is RC. Is that clear? RC by calculation it comes out as 150 ohms, and therefore in this circuit this is determined, this is known, RL is known. All that now one has to determine is RE, this resistance. Can you see this diagram? Is this okay? Visible from the last page? Yeah. You have to determine RE, R1 and R2. Then the design is complete. Alright. Now to determine RE, to determine this resistance, now we do not know RE. Do we know I sub C? Yes, we do. What is I sub C? I sub C is 0.2 ampere or 200 milliampere, and therefore we have to arbitrarily fix V sub E. This is a situation where RE is not known, and therefore we arbitrarily fix VE, and we can take any value that we like. We still do not know what is VCC, and therefore arbitrarily let's put a few volts as VE, and typical figure is 3 volts. You can choose 4, you can choose 2, there is nothing sacred about it, provided you choose beta, you choose RB, that is R1 parallel R2, that has to be chosen as beta minimum times RE divided by 10. Alright, at least. It could be greater than this. Okay. So what we do is we assume that VE is equal to 3 volt. Then what is I sub E? I sub E is 200 milliampere, okay, that is 0.2 plus I sub B. Now you can see this. What is I sub B at the Q point? It is 4 milliampere, that means 0.004. Is that correct? Which means that 4 milliampere can be neglected compared to 200. The calculation will not be absurdly upset by this negligence. Alright, and therefore we say I sub E is 0.2 ampere, which means that RE shall be equal to how much? 15 ohms? 15 ohms. Now do not be surprised at this low values of resistance, because it is a power amplifier and your idea is to deliver power, maximum power, to a load as low as 750 ohms. Alright, and therefore RE has come out as 15 ohms. If RE comes at 15 ohms, then what is RB? RB shall be beta minimum. Beta minimum was specified as 30 times RE, that is 15, divided by 10, which is 45 ohms. Alright. So, and this is equal to R1, R2 divided by R1 plus R2. Alright. This is one of the equations. And the other equation would be determined in terms of VBB. But to determine VBB, we must first find out VCC. What is the power supply needed? This characteristic curve gives no idea about the power supply that is needed. Does it? Or does it not? Since you know R sub C and you also know RE, don't you know the DC load line? Okay. In fact, this line, this orange line, is the DC load line. It goes right up to some 58 volts. Is the point clear? You can get what VCC is needed right from the characteristic curves. Why? Because RDC in the circuit, RDC is simply RC plus RE, where we have ignored the I sub B component. All right. So if you draw a line at Q with a slope of minus 1 by RC plus RE, which is 150 plus 15, that is 165, then that will be this orange line, and wherever the orange line cuts the VCE axis shall be equal to VCC. Is that clear? And therefore we know VCC. If that doesn't appeal to you, if you prefer to calculate this, all right, you do calculate. VCC shall be I sub C, R sub C plus VCE plus I sub C plus I sub B times RE. And you can see that I sub C is 0.2 ampere times R sub C is 150 plus VC is how much? No, VC is 25 volts. So 25 plus I sub B plus I sub C plus I sub B. Well, take it as 0.2 multiplied by RE is 15 ohms. So how much is this? This is 58 volts. Well, that's what the diagram also gave you. 58 volts, approximately 58. Okay. So you know VCC. Now, therefore, VBB is equal to VCC 58 multiplied by R1 divided by R1 plus R2. You can also calculate VBB from the base circuit, that is equal to IB. What is IB? 4 milliampere. So 0.004. 4 milliampere is that okay? 0.004 multiplied by RB. We have already chosen RB, that is 45 ohms. IB RB plus VBE is 0.7 plus VE. How much was VE? 3 volts. And this you can see how much is this? 3.7 and 0.18. So 3.9 3.887. Yeah, okay. Actually it should be, we ignored that I sub B here. If we had not ignored, it would come to about 3.94 or so. Whatever it comes. there is a figure, alright. So we know VBB, and therefore we have two equations. One is 58 R1 divided by R1 plus R2 equal to 3.94, and the other is R1 R2 divided by R1 plus R2 is equal to, how much was this? 45. So all you have to do is divide this equation by this, then you get R2, and if you know R2 you can get R1. The final values are R2 equal to 680 ohms and R1 equal to 47 ohms. This illustrates what an electrical engineer does when he is required to design a power amplifier. The point is, how do you choose the transistor? Well, suppose somebody says, well, I want a power of, I want a 5 watt power amplifier, okay? That is a power amplifier which can drive 5 watts into a 750. How much power in this case we get to the load?
5 watts.
Do we get 5 watts?
No.
Load power. Yes, what is the load power? How do you calculate the load power? Let's look at this again. The swing, the voltage swing in 750 ohms would be approximately 25 volts. 25 volts, alright. So 25 volt, what is the root mean squared value? This is the peak value divided by root 2. This is V, let's say small c, that is the RMS value of the voltage across the load. And what is the power then? Power is Vc squared divided by RL. What is RL? 750 ohms. So how much is this? 625 divided by 750 multiplied by root 2 multiplied by 2. You see how poor this circuit is. It is approximately, it's even less than less than 0.4 watt. 5 watts is being dissipated in the transistor. And by driving the transistor to its limit, we can get only 0.4 watts. So it's very inefficient. Isn't that right? It's not even 10%. From 5 watt we are wasting, and we are getting 0.4. All right. The maximum that can be obtained under this condition, the maximum efficiency, this will be a tutorial problem which will work it out in the tutorial class, but the maximum efficiency, you take it from me, is 25%. For such operations, the maximum efficiency of a power amplifier is only 25%. So if you want 5 watt load, 5 watt into the load, the transistor that you will select should be able to dissipate a minimum of 20 watts. And you see, we could get only 10% or so efficiency here, and therefore to be on the safe side, in order not to burn the transistor out, you choose a transistor which is not 20 but let's say 30 watts or 40 watt transistor. Then you are safe. Alright, the stereo amplifier will not burn out in the middle of a music or in the middle of a speech. Alright, so that's where you start from. After you choose the transistor, the main consideration for the transistor is how much power it can dissipate, depending on what power you want in the load. After you do that, then you take the characteristics as specified by the manufacturer and go ahead and design this circuit with the various resistances and so on. Now you got a resistance like 15 ohms. Fortunately 15 ohms is manufactured by the manufacturers, but suppose you had 45. 45 is not manufactured. The closest resistance is 47. There are some preferred values of resistors, preferred values of capacitors that are manufactured. So you will have to go to the stores, take, let's say if you want a 1K resistance, 1K is manufactured, but who knows, 1K, the 1K that you take may have 10% tolerance or 20% tolerance. So you take a bin from the storekeeper and go on measuring, and you match the requirement. You take a dozen, maybe one of them will fit your prescription. So there are compromises all throughout. The design process is such. what we do analytically is not exactly reflected in the laboratory because there are limitations, there are tolerances. And if you achieve, let's say if the specification is 5 watt and if you achieve 4.9 watts, you will say, I have done a good job. You might also get 5.1, then you are happy. Alright, because the errors might accumulate in the favorable direction and may give you a power more than what you want. Alright. Now in the circuit that we have discussed so far, one of the reasons that you do get so poor an efficiency is because some power is wasted in RC. You don't want power to be wasted in RC, you want all power to go to RL. And therefore, if you had a means of transferring power to the resistive load without any intermediate resistance, then it would have been very nice. You would be able to save some power. You would be able to increase the efficiency. And this is what is offered by a transformer coupled power amplifier. If you couple the load to the transistor through a transformer, then you derive 3 benefits. But before looking at the benefits, let's look at the circuit. The circuit is like this. Instead of an RC, what you have is a transformer primary in the collector circuit. This goes to plus VCC. There is no RC. The collector goes straight to the primary coil of the transformer. The transformer has a secondary, and it is to the secondary that the load is connected. The load RL is connected to the secondary. So there is no intermediate resistance through which the load is connected. In the previous circuit, there was a resistance R sub C. Why was R sub C needed? Could we make R sub C equal to 0? Just a minute. Could we make this R sub C equal to 0? Could we? If we had made R sub C equal to 0, what would be the effective AC load? 0. RL parallel short circuit is a short circuit. So there was no way I could get rid of R sub C. But in this circuit that you see now, there is no R sub C. There is a small amount of resistance here in the primary of the transformer, but that would be several ohms, and you can ignore. We shall assume that this transformer is a perfect transformer. That means it has no resistances in the primary or secondary. A few ohms should be tolerated, alright, a very small dissipation, but otherwise you can assume it to be ideal. So the load power is transferred to the load without getting wasted in the via media. The via media is a transformer, alright. Not only that, it has another benefit that that capacitor that we had to use in the previous circuit is no longer required. Or the price that you pay is a heavier block. A transformer is a larger block and a heavier block. But it avoids the use of a capacitor. It isolates the load from the DC. Alright. It isolates the load from the DC. Why? Because it is only varying currents that are transformed. A steady current is not transformed. Alright. So first was no dissipation in RC. Second is isolation of DC, and the third and the most important is that a transformer allows a matching. Maximum power transfer theorem says that the load should be complex conjugate of the source resistance, alright. So with this transformer, by varying the turns ratio N1 to N2, you can so design that the effective load that you see in the primary RL prime may be the maximum, may be the condition for maximum power transfer. That is, it may be equal to, if you take the Thevenin equivalent, it may be equal to the Thevenin equivalent resistance looking back at the transistor. Then you are sure that maximum power is being transferred to the load. Alright, so these are the 3 basic benefits. Now if I complete this circuit, I must have an RE here, I must have an RE, and I must have a CE in parallel, which is a bypass, and in addition I must have the usual R1 R2 combination, the usual R1 R2 combination. Now where from shall you take the R1 and R2? From here or from here? From VCC directly. Why? Pardon me? No. Yes. If we take it from here, then we include some resistance here, the winding resistance. We don't want to do that. So we connect directly from here, and I shall simply show the equivalent circuit. Equivalent circuit is that you have an RB and a VBB, which is equal to VCC R1 divided by R1 plus R2, and RB is the parallel combination of R1 and R2. And the signal, let me show this as a signal, as a current source. The input signal is here, I sub I. This current is I sub B, the DC current, and this is the total current, I sub small I sub capital B. This is the total circuit. Well, not quite, because I have shown here the equivalent Thevenin's circuit. I should have drawn R1 from here to the base and R2 to ground. Instead of that, I have shown the Thevenin equivalent circuit. Now, how do I analyze this circuit and how do I design this circuit, the transformer coupled amplifier? The advantages, as I said, are three, and as you shall see, the maximum theoretical efficiency of this is 50%. 50%. That means if you take a 5-watt transistor, you can deliver in theory 2.5 watts to the load. All right, we will see this. We will see this by analysis. Now, if you recall circuit theory, the transformer, the perfect transformer, has the property that if V1, now I am showing phasors, V1 be the voltage here, the current is I1, I am omitting the bars, and this is I2 and this is V2, the turns ratio is N1 to N2, then you know that V1 by V2 is equal to the ratio of the turns, that is N1 to N2, and it is also equal to the ratio of the currents I2 to I1. Is that correct? No, there is a big mistake in this. There is a minus sign here. Why is the minus sign required? Because the total power absorbed by the transformer is 0. So V1 I1 plus V2 I2 should be equal to 0, and this is how this relation is obtained. V1 I1 shall be equal to minus V2 I2, and there is a negative sign here. Not only that, if you recall, if there is a resistance R2 here connected, then what is the effective resistance R1? It is simply it is V1 by I1, correct? And V1 from this relation is N1 by N2 times V2 divided by I1. I1 is minus I2 N2 by N1, which is equal to N1 by N2 whole squared multiplied by V2 by minus I2 is simply R2, and this is how the transformation is affected. That is, if you take this resistance, if you terminate the secondary in R2, then what you see in the primary, it's called reflected resistance. This resistance reflects itself to the primary with a factor of N1 by N2 whole square, that is the turns ratio whole square. For example, if you require for maximum power transfer a 1K resistance and your speaker is 8 ohms, then obviously N1 by N2 squared should be equal to 1K, that is 1000 divided by 8. So you can choose your turns ratio properly. All right, and this can be made very easily with course available in the laboratory. So this is the basic relationship of a of a transformer which you shall utilize, and to illustrate the design of a typical circuit, we will take a very simple case. Is this clear? Yeah, I think so. We will take a typical characteristic. Well, you see, this is also a plot of I sub c versus VCE, all right, and there are several things now which one has to be very careful about. You see, in the transformer coupled amplifier there is no RC. The DC load therefore is simply RE plus the small winding resistance of the transformer. Small means several ohms, and in a power transistor you have seen in the previous case that RE is of the order of 15 ohms. You don't want a large RE, because then RE will itself waste power, isn't that right? So in a transformer coupled amplifier, RE should also be a small quantity. In other words, you won't choose VE equal to, if the power supply is, let's say, 12 volt, you won't choose VE equal to 3 volts. You would choose VE equal to 1 volt or maybe 0.5 volt, because what matters is RB should be beta mean RE divided by 10. All right, so there is a flexibility. In other words, the DC load line is almost a vertical line. Is the point clear? DC load line is this green line. There is a slight slope here because of that small resistance, but actually in practice there is very little difference between VCC and VCE. It is almost a vertical line. Is the point clear? If the transformer was ideal and there was no RE, then the line should have been a perfect straight line. It is slightly inclined because of RE, so the slope is minus 1 by RDC, all right. And the Q point, therefore, it's very easy to find the Q point. What you do is you find the maximum dissipation hyperbola and draw a vertical line at VCC. Wherever it cuts is approximately the Q point. If you want to be fussy, then you shift the Q point, you actually draw the DC load line and find out where the Q point lies. But it is clear that VCE and VCC are very close to each other. Is this point clear? Then what should be your maximum swing? Approximately twice VCC, all right. And the slope, the AC load line shall now be whatever resistance is seen by the primary. AC load line shall be determined by RL prime, all right. AC load line slope shall be minus 1 by RL prime, because RE is approximately 0, winding resistance approximately 0, and therefore on these characteristics you draw the AC load line. Well, the AC load line, obviously if the Q point is fixed, if the Q point is determined, then you know its vertical intercept is approximately VCE, and therefore you go another VCE distance, all right, and then you find out the slope, as you did in the previous case. In the previous case we found this out to be 125 ohms. You remember how we did that, all right. So you know the slope minus 1 by RL prime. Now you have to be careful. Once you have done this, what I have shown here is Q point is at small ib equal to capital I sub capital B, and we said the swing would be limited between 0 and twice IB. Obviously we cannot exceed that. If this is your Q point, you go IB on this side, then you must come down IB on the other side also for no distortion, all right. You must allow equal swings. The point, however, is that you cannot exceed this point. You cannot go down below this. Why? Because this is the curve IB equal to 0, and you cannot go beyond this point. Why? Because this is the saturation region. This is a highly nonlinear region, and we shall not permit the transistor to go beyond this. So there is a V min, there is a minimum value of V min. We cannot go exactly to 0, and there is a V max. Vmax is not equal to twice Vc, it's slightly less than twice Vc, and Vmin is slightly greater than 0. Okay. What about the current swings? At the Q point the current is I sub C. Now the maximum that we can go is this knee, this point, and we call this I max. The minimum that we can go is this much, which is I min, alright, capital I min. I min is not equal to 0. These are facts of life, and one is to live with them, alright. Now what guarantees that this swing is equal to this swing? No, there is no guarantee. Isn't that right? This distance may not be equal to this distance. Okay, so you'll have to choose the smaller of the two. Is that clear? Similarly, VCC, I'm sorry, this is VCE. VCE minus Vmin may not be equal to Vmax minus VCE. You'll have to choose the smaller of the two. Alright, but one thing is clear that the swing, the peak to peak voltage swing between collector and emitter would be approximately Vmax minus Vmin divided by 2. Agreed? Similarly, the peak to peak current swing shall be Imax minus Imin divided by 2. And if you know not peak to peak, the peak value, peak to peak is Vmax minus Vmin, divided by 2 is the peak value of the swing, and if you know the peak value, divide by square root of 2 to get the RMS value, alright. And therefore we can very simply write the RMS value of the load voltage, the RMS value of the load AC voltage, V sub C, this is small c, not capital C. If it is capital C, then it's the DC. Capital V sub small c is simply V max minus V min divided by 2 root 2. Similarly, the RMS value of the load current I sub C shall be I max minus I min divided by 2 root 2. And the power in the load shall be simply the product of the two, that is Vc times Ic, or you can also write this as Vc squared divided by what? The effective load, RL prime, or this will also be equal to Ic squared times RL prime. Either way, any of these three relations will give you the power that goes into the load. Alright, this is the load power, this is the AC power, signal power delivered to the load. What is the power that is supplied by the source, the battery? Let's call that power as PCC. This is obviously VCC multiplied by I sub C, and VCC is approximately equal to VCE. Is that correct? This C is capital, this C is capital. VCC is approximately equal to VCE. Why?
There is no resistance.
There is no resistance in the collector except for the small winding resistance, and the emitter resistance is also a very small quantity. So this approximation is usually valid. And under this condition, therefore, let us find out another quantity, that is the average power dissipated in the transistor, and we shall have fun. How much power is dissipated in the transistor? Obviously, the instantaneous power dissipated in the transistor is VCE, the total collector to emitter voltage, multiplied by I sub C. Alright, this is the instantaneous value. So what we will do is we will integrate this over one period of the sinusoid, let us say d theta, where theta goes from 0 to 2 pi, theta is equal to omega t, and then we divide by 2 pi. Is that okay? Where we have assumed sinusoidal variations. Now, if I assume that I sub c, the total collector current, is equal to the DC collector current plus the AC collector current. AC collector current would be root 2, not input current, the collector current, the current in the collector. Okay, it will be root 2 I small c, the RMS value, times sine of omega t, which we have put equal to theta, sine theta. If I sub c is taken as this, is the point clear? The total collector current has a DC component, the quiescent component, and an AC component. DC component I represent by I sub capital C, and the AC component is Im, the maximum value, which is root 2 times the RMS value. We have already calculated the RMS, sine theta. Then what should be VCE under this condition? It would be the DC value, capital V subscript capital CE, and then, yes, plus the AC value, which is root 2 VC sine of theta. What would be the sign between the two quantities? Why? Out of phase. Yes, that's right. When the collector current increases, the collector to emitter voltage decreases, and therefore this should be a minus sign. Now, if you carry out this algebra and the integration, then the result becomes very revealing one. What we get is, by calculation, V sub d, P sub d becomes VCE times I sub c minus Vc times Ic, as simple as that. And this is a very revealing relationship. It should have been clear from common sense. Alright, VCIC is the power delivered by the battery, and this is the power that is transformed into signal power and is delivered to the load. So the total power supplied by the battery minus the power supplied to the load, signal power, must be the power dissipated in the transistor. Alright. So, and this also shows something else, that if you do not apply a signal, that is V sub c equal to 0 or I sub c equal to 0, then obviously the power dissipation in the transistor shall be maximum. Alright. So before the political leader comes, you should not put your public address system on, because it gets more and more heated. Is the point clear? When there is no signal, the power dissipation is maximum. Not only that, when you are delivering maximum power to the load, the dissipation in the transistor is a minimum. Alright. So it is not good to put a power amplifier on without a signal. It is only after the signal has arrived, it is better to put the power amplifier on. Otherwise, unnecessarily you waste heat. Now comes the question of efficiency. Well, efficiency eta is simply equal to power to the load, signal power to the load, V sub c I sub c, divided by VCE I sub c. Alright, and this usually is multiplied by 100 and expressed in percentage. What would now be the maximum possible efficiency? What is the maximum possible VC? The root mean squared value. What is the maximum possible VC? If that takes time, pardon me, root 2 times, how is it related to VCE? Pardon me? That is correct. The peak value is VCE, so it is VCE by root 2. And what is I sub c, maximum possible value? capital I sub c divided by root 2. If conditions are ideal, that means if conditions are like this, that is, if we can approximate the transistor characteristics by straight lines, okay, the saturation line is the vertical line, IB equal to 0 line is the horizontal line, and then in between there is no nonlinearity. If they are perfectly straight, this is the most ideal condition, then VCE would be equal to VCC and the swing would be up to 2 VCE. The current would go from 0 to twice IC, and this is the most ideal condition. And under this ideal condition, this is what shall be valid. That is, VC would be VCE by root 2 and IC would be IC by root 2. And you can see that this is equal to 50%. This is the ideal efficiency of a transformer coupled amplifier. The usual values that we get in practice surely should be less than 50, but it is a very encouraging thing that 40 to 45% of efficiency can be obtained even by the most negligent designer, which means that even if you have lot of tolerances in the transistor, in the design, all right, if you are not very careful, even then 40 to 45% with a transformer coupling is very easily obtained. Well, the price that you pay literally is the price of the transformer. A transformer is much more costly as compared to a capacitor and a resistor. A resistor may be a rupee, capacitor may be 5 rupees, a good capacitor, 5 to 10 rupees. But a transformer may be about 80 to 90 rupees, a good transformer. Well, you have to pay a price to get a good performance. Next time we shall take an example and go to other types of operation of a transistor.